We just mentioned the microscopic system of Isaac Newton. On the other end, there's the macroscopic point of view, which we talked at length in the beginning of this class in terms of its history. As a reminder, in 1748, in the Academy of Sciences in Berlin, announced a prize for 1750 regarding the resistance of fluids when rigid bodies are immersed in them. D'Alembert took part in the competition and submitted a manuscript which was revolutionary. For the first time, in a movement of a fluid described by partial differential equations, which is what partial differential equations were invented for by D'Alembert anyway, acting on the velocity of the fluid. Unfortunately, this model wasn't exactly correct, of course, because it did not contain viscosity terms. And the final equations were coined by Leonhard Euler. That is, if U is time-dependent and space-dependent, that is the velocity, and three-component vector field denoting the velocity of the fluid, it can be solved by the following system of partial differential equations in equation 172. These are the Euler equations, of course. This is the D'Alembert condition, and this is the Euler equation itself for compressible flow. Now, D'Alembert quickly realized that a solid body placed in a fluid satisfies these equations and can evolve without suffering any resistance. That is, there's no drag. You can look at his original paper where he has placed a small body in 2 dimensions and left this paradox to future researchers like Euler. He was busy with other things in life anyway. To understand why the solid body is submitted in general to a force tending to slow down, one needs to put in friction and resistance at a molecular level. That is, the first coefficient of viscosity was missing from the model initially, from the incompressible case at least. The fluid will have a tendency to dissipate energy under heat and acoustic radiation. Obviously, this is absent from the Euler equations, and in 1820, Navier had the idea of putting in an additional term to Euler's equations, which appears here in equation 173, which is the viscous term. George Gabriel Stokes, in 1845, formalized all this mathematically, amongst many others who attempted it, as I talked about in the history section of this class, and found this incompressible form of the Navier-Stokes equations. Here, nu is the first coefficient of viscosity, which is greater than 0, and it measures, of course, the discrepancy between viscous fluids and so-called perfect fluids or Eulerian fluids.